Now that we've talked a little bit about equilibrium reactions, let's take a look in more detail at the equilibrium constant. The equilibrium constant expression for any reaction, such as this generic one shown here, is equal to the concentrations of the products raised to their stoichiometric coefficients divided by the concentration of the reactants raised to their stoichiometric coefficients. And this K value is a constant, but it does vary with temperature. So what that means is that for any given reaction, there is a set ratio of products to reactants for equilibrium equations that varies with temperature. Okay, so if you know K for a certain temperature, it will be the same no matter what. So let's do some practice here. So we have N2 and 3H2 going to 2NH3, CO, half O2 going to CO2, and 2CO2 going to 2CO and O2. So if you'd like, pause, write down your equilibrium expressions, and then let's see if we are correct. So here we have our ammonia. It is our product, and it is on top of our ratio, and it's raised to the 2 because of this stoichiometric coefficient here. Nitrogen gas is, it's not raised to anything because it's just, the coefficient would be 1, so you could imagine there's a 1 here. And then our hydrogen is cubed. It's raised to the 3rd power because of this stoichiometric coefficient here. For this expression, we've got our carbon dioxide on top and our carbon monoxide and oxygen on the bottom, whereas oxygen is raised to the 1/2 power. And then finally, for this third one here, we have carbon dioxide squared is on the bottom. It is our sole reactant. And then on top, we have our products, carbon monoxide squared and oxygen. So writing this out is really simple. The only things that you have to remember are that you need to include the stoichiometric coefficient in your equilibrium expression, and that these are concentrations. Okay, so we will be setting up an equilibrium expression for many practice problems in the near future to give you some chances to work with this. So let's think about what this equilibrium constant tells us, what it actually means. So here would be a composition at equilibrium. So let's imagine there's this reaction where under this scenario, your reactants are this purple ball, and then the product is a orange diamond. And this is the composition at equilibrium. So at equilibrium, we still have mostly reactants around. This is the scenario when K is very small, and we usually mean if it's under 0.001 or 10 to the minus 3. This tells us that our equilibrium, we would say, lies to the left, or it favors reactants. If we have an intermediate scenario where we have roughly equal amounts of reactants and products, this is where we have somewhere between 10 to the minus 3rd and 10 to the 3rd, then we have a significant amount of each. So we can reasonably, they both are reasonably contributing to that K value. When the K value is very large, it tends to favor the product side, or we would say equilibrium lies to the right. And in this scenario, the product is the dominant form, not the reactant. So let's take a look at what we might expect to see with these reactions here. So with this one here in black, it's a very small equilibrium value. So this means that we're going to favor the reactant. So a small k means the reactant is favored, and at equilibrium, the equilibrium we say lies to the left, there is mostly still reactant around. Reactions 1 and 3 have a K value that's pretty close to, it's in between -1,000 and +1,000, so it's just, it's not even 100, so it's pretty close to 1. And what this means is that at equilibrium, we would have roughly equal amounts of both. Now, they won't be identical, but we would have similar amounts of both reactants and products. And that's true for 1 and 3. For reaction 4, with a K value that's very, very large, we say that the reaction favors the product, or the equilibrium lies to the right. So if we were to look at the equilibrium concentrations of both of these species, we would see that the equilibrium concentration for oxygen was significantly higher than that for ozone. For reactions with gases, we can also use partial pressures instead of moles per liter, because sometimes it can be hard to think about the concentration of gas in moles. If you're going to use partial pressures instead of molarity, then you have to have this Kp value, and that's where you take the ratio of the partial pressures raised to their stoichiometric coefficients. So what this actually means is it's like an effective pressure, which is the ratio of the partial pressure compared to the standard state of 1 bar. 1 bar is very close to 1 atmosphere. If you're not comfortable thinking in bars, just think 1 atmosphere. It's roughly the same. So Kp is not the same as the K, but it is related, and we'll see that in a second. So these two values get related by the ideal gas constant. So Kp, if you're going to use partial pressures, is equal to K times RT raised to the delta N, where our R value is 0.08206 liter atmosphere mole Kelvin. So this is the ideal gas constant. So watch the units. Make sure you're using the one with the correct units. So you want the liter atmosphere mole Kelvin one. T is the temperature in Kelvin, and delta N is the change in moles. So this would be the moles of product minus the moles of reactant. So let's do a practice problem. So we have 2 moles of NO gas and a mole of oxygen gas reacting in equilibrium to form 2 moles of nitrogen dioxide. The Kp, so the K found with partial pressures, is 2.2 times 10 to the 12th, and the temperature is 25 degrees Celsius. So we're given Kp, and we want to find K, and we know this equation here. So we also need to put temperature into Kelvin and then calculate delta N. And our delta N is 2 moles minus 3 moles, because that's how many moles we have on the product side is 2 and the reactant side we have 3. So our delta N is -1. So now we know our Kp value. We can divide by that RT raised to the delta N to get our K. And when we do that and solve this, we get 5.4 times 10 to the 13th. So now that you've been able to see a couple examples of how we work with our equilibrium constant, go try some more practice problems on your own and try and cement these concepts.